Okay, hey everyone, good afternoon. I hope you're having a great day so far. This has been a really exciting conference, really great content so far, and I'll try to spend the next hour with you on some talk about concurrency and about like new additions to the C++ standard that relates to concurrency. So my name is Roy Barkan. I live here in Tel Aviv. It's great being in this conference and this venue again. I've been doing C++ for quite a long time, and a big portion of that is with Istra Research. We're a high-frequency trading company also here in Israel. We're always looking for great talents. If you want, you can catch me up later, and we can discuss how you might find your way to doing high-frequency trading with Istra. And I've been doing these conference talks for about 5 years now, and I also really enjoy it. I mostly learn as I prepare these talks, but also as I give them by your questions, so feel free to ask questions. It'll make this whole thing more interesting. This is a link to the slides if you like, especially if you're sitting in the back, you can try and get them. So today we'll talk about concurrency. I'll give you a short introduction into what concurrency is for programming systems, for programming languages, why people use them, what's the main reasons for that, and different ways or techniques for creating a system that is concurrent. Then we'll spend most of our time discussing the notion of structured concurrency. This has been a relatively popular concept for methodology for writing concurrent systems that has risen in the past 4 or 5 years now, I think, maybe a little more. And it gave rise in other programming languages and entered C++ as well. So I'll let you give you a little bit of an introduction of what structured concurrency is and what are ways for us to write structured concurrent code in C++ today and in the future. And then we'll spend some time talking about migration. How can we take concurrent systems that were implemented or written before notions of structured concurrency were in place, and how we can maybe try and take existing systems and migrate them towards these new notions and ways to do it. So concurrency in software systems, again, typically, especially if you go back to the 50s, 60s, and 70s, computers and algorithms were first sequential. There was not much thought to concurrency. An algorithm was a set of instructions, and typically if you think of dependencies, you could really think and rely on the fact that every instruction depended on all its predecessors. Before the instruction started, everything that preceded it already took place, and it was totally okay for an instruction to depend and rely on the results of the previous instructions. But even in those early days, it was apparent that the environment that we work in is not so simple. Although we were thinking about algorithms in a sequential manner, the world that we live in is not as simple as that. First of all, in terms of compute, even in the 70s, and obviously today, we have multiple processors, a lot of computation that can happen in parallel. We can assign different instructions to run on different places, even at the same time, and thus relying on dependencies and relying on everything that happens that's written before us to take place so far means that we might not be able to exploit parallelism that exists in our computing infrastructure. And also when it comes to inputs and events that coming in, it was pretty clear very early on that systems themselves were not just monolithic pieces of code that received one input, worked on it, and generated one output. Systems are things that live for a long time, and their inputs are longer running. You have just a stream of events coming in. You need to deal with them one by one, and it's not always certain what the sequence of events coming in might be. I cannot really tell what might come in before, what event might come in before any other event, and for that reason, the exact sequence of operations that I might need to my computer system to handle might not be very clear-cut and known in advance. Things are concurrent in the world in their nature. So when I create a system that has these multiple inputs and multiple events that might come in at different unknown orderings, those requests can be totally unrelated or they can be linked. Unrelated events is, for example, if I have a web server that receives many requests from many different clients, each client is unrelated to each other. I do not know which event might come before or after another one, but they're totally or supposed to be unrelated, so I shouldn't really care about whether I handle the first one or the second one first. I try to deal with them in the order that they arrive. But sometimes events are linked. Right after I put in money in my bank account, I want to check the amount of money in the account. Obviously, I need to make sure that those two events are linked, and I handle the second one only after I completed the first. So again, systems in today's modern system are something that might have many threads, many computation cores that run in parallel. Events also come in from many clients, and I need to somehow try to write my code in a way that handles these complicated scenarios. So that's software systems. If we try to write code that deals with concurrency, what does that mean? And basically, I think the main thing is that concurrent code is code where we can more easily define what the dependencies are between our different components or between our different instructions. If without concurrency, I know that every instruction might depend on everything that came before it. With a concurrent system or a coding system or a coding environment that lets me express concurrency is one where I can write different instructions and specify to the environment or to the computing infrastructure what the actual dependencies are, and basically I can express the fact that not everything relies on everything else. And typically, if I have a system that tries to create those things, I have various building blocks that I can use. One very common building blocks is what's called a non-blocking API. A non-blocking API is a function call that I call, and when the function returns, I know that the result or the effect of the function might not be already over. Okay. For example, if I want to read something from a hard disk, or wait for or look up for an event coming in from a user or from an external actor, I can have an API that doesn't block, doesn't hold anything up for the CPU while we're waiting for the event. The function returns immediately, but something in the background is waiting for the event to happen. And when I do that, I need to obviously deal with it. And one way of dealing with it is what's known as like a completion callback, where I can specify to that non-blocking API, hey, when you return, nothing's already, no information is ready yet. Here's the callback. Here's a function or a piece of code that I want you to run that is the actual dependencies that I do want to happen only once the event arrives. This approach of sending in callbacks, sometimes called the continuation passing style. The callback is the continuation, is what needs to happen once the event happens. And I pass the continuation to the async non-blocking API, and it should be in charge of invoking or triggering that continuation once the actual event arrives. Obviously, as we mentioned, the return code or the return value of this non-blocking function will not be the event itself, because the event itself didn't happen. So basically what I typically would receive back is some sort of an identifier and not the result. The identifier is sometimes called a future, and that future is something that I can use to maybe still wait for the result or check whether the event arrived, etc. Another building block that is sometimes discussed is the notion of a fork, taking one sequential stream of instructions and splitting it into two. You can think of it as sort of like a generic non-blocking API that doesn't really wait for an event, just starts a continuation in parallel with whatever I'm doing right now. So the event is sort of considered like an event that immediately happens, and I start running its continuation, but I can potentially do it in parallel with the work that I'm doing in my own main thread. When I'm saying fork here, I don't mean the operating system level notion of a fork. Just any time a single stream of instructions can be split into two, and I can tell the coding environment that I'm in that these two streams don't really rely on depend on each other. They can run in parallel. That's what a fork means. And in C++, there are already mechanisms that implement this notion of a fork. using the sometimes thread or thread pool mechanisms, such as stood ::j thread and stood ::async. And basically, when I use these mechanisms, I can specify a different piece of code that can be run in parallel, and I tell the C++ infrastructure that there is no dependency. The current stream and this new stream can run in parallel or can run in any order that the system likes. Similar to a fork, we also have a join. The join operation is one where I specify, hey, this stream that I'm on, I do not want it to continue before some other stream is complete. Okay, I want to make sure that that whatever I'm doing right now will not continue until some other thing is complete. This is the way that I actually say that a dependency does exist. And some finer-grained ways of describing dependencies are things like mutexes, semaphores, barriers, etc. And those are other more fine-grained ways of having different streams that typically don't have a lot of dependencies between them, but have minor dependencies or minor critical sections that need to be dealt with, so those mechanisms can be used. Another notion that sometimes has to be taken into account or that exists in those concurrency environments is the notion of cancellation. Sometimes if I have some stream of operations that happens in parallel to myself or can happen concurrently, and I realize that I do not really need its result. I do not actually depend on it. Nothing depends on it. Some frameworks or systems let me describe the notion of cancellation, where I can basically tell the framework that I'm running in that there's no need for a certain result, for a certain stream, although it's been created. And if the system is very, very efficient, it can try and eliminate or don't do extra work when it's not needed. And again, in C++, as of C++ 20, there has been some start of notions that deal with cancellations. Those things as stop sources and stop tokens are mechanisms that were added to the language initially for threads, but they're also being used for other asynchrony and other concurrency mechanisms to try and specify that cancellation might be needed. There's no actual dependency for a certain stream. It might as well just stop. Okay? So again, typically with those building blocks, we can create these massive chains of dependencies of different streams that can run in parallel or wait for each other. Those streams typically, they can be thought of as direct acyclic graphs, and I can think of my algorithms as these types of flow machines where information flows, in this example, from top to bottom. Okay, so we have these building blocks, and we can use them to write our system in a concurrent manner. Again, what's the point? Why are we even bothering with this? So again, because the first reason is to exploit parallelism. If we have multiple computer environments, if we have not just a CPU, but also a GPU or some networking system or disks, or maybe multiple CPUs, I want to make sure that I can keep them all busy at the same time. I want to make sure that if one of the subsystems can work in parallel with the other, I want ways to tell my environment that this is what this is what I want to be done. So I want mechanisms to say it. Another really important motivation is separation of concerns. Sometimes if I have a system that is inherently concurrent, runs on a single server, but does separate things that don't really depend on each other, if my environment lets me write the system in a way that those different streams of operations that don't depend on each other can be written totally separately without really thinking about each other, the code can be simpler. Okay, so I can independently develop each and every component that doesn't depend on each other without really thinking about the side effects or the potential clashes or collisions that might happen because events of one of the streams might happen in tandem with the events of the other stream. Also, when I have one single system running many multiple event handlers and many concurrent operations, there's suddenly some considerations that need to be thought about priorities, about fairness, about scheduling. Because sometimes I have a case where my system might demand or might exploit more resources than are actually available to me. And a good concurrency system is one where whoever writes the concurrent systems not need to bother themselves too much about how the allocation of all the different existing compute resources are basically allocated to other requirements. And I can have a separate team, a separate person implementing the scheduler or implementing those mechanisms that know how to do the context switching or priorities and decide what needs to run in case there's more desire than actual resources for that. Another motivation for writing concurrent systems is for hiding tail latencies. Sometimes there are ways that I can achieve the exact same result by doing it in multiple different ways. Some of them are maybe typically faster than others, but can have tail latencies or might have cases where they're slow. So a good concurrent system will allow me to create these races where I can initiate two different types of computations in parallel. I can go to Google as well as to Bing, or I can go to one LLM as well as the other. And once I get a good result from one of the services, I can just cancel the other one. This is more exploitative of computational resources or resources that I have, but it can really improve my system performance, and sometimes that's what I need. And another motivation that can sometimes be helpful when writing concurrent systems is the notion of batching or chunking. There are cases, I think it's very, very common, for example, in hard drive systems, where if the peripheral itself, or if the component itself, or database itself that wants to perform operations or knows in advance a complete batch of everything, all the pending requests that need to be done, it can decide how to optimally rearrange them and do them together. So again, a concurrent system where I present all the different unrelated tasks that I expect my hard drive or my database to do together will allow that peripheral to actually look at all of them together and maybe achieve extra efficiencies because it is aware of all the requests coming in from my system in a parallel fashion instead of just one by one. Okay, so these are the different separate various motivations. Here's a nice Gemini created slide that tries to show this notion of a race between various approaches that I can cancel once the first one wins. Now that I know what concurrent building blocks I have and hopefully decided that I want to write a concurrent system, what are the main categories of ways of writing one? How do I approach creating an architecture of a concurrent system? So one of the very common approaches that was very, very popular, especially in the early 2000s, was relying on operating threads or even operating system processes. The operating system, as you know, is basically in charge of dealing with security, dealing with running multiple unrelated things in parallel anyway. It's all things that typical operating systems do. They have preemption, so if one stream of operation decides that it wants to hog the resource, the operating system can know to stop it to give some more fairness or more priorities to others. The notion of context switches is supported both by the operating system and by hardware typically, so it's very easy and very simple for a single process to run and unknowingly be preempted, stopped, go through a context switch and return without much hassle, without much complication to whoever writes that single process code. So it's a very, very simple approach. In C++, it's supported by the standard in a portable manner since C++11, very, very common, but it has its downsides as well. I think the main downside is the high overhead. Okay, operating system is something that's relatively far away from our code itself. It doesn't know a lot about our process, so when it decides to take our process and move it from a running state to a waiting state, or when it decides to get the process to wait for a disk or some other peripheral, the OS doesn't know a lot about us, so it needs to perform a lot of maintenance to make sure that it does everything right in a good manner, and the overhead is hard. And this approach is known to be very, very unscalable. If I have a system with, for example, 20 or 60 or 100 CPU cores, and I want to run 1,000 or 10,000 or even 100,000 threads, this is something that operating systems typically cannot handle. This is not a scalable thing. If I have many, many concurrent threads of operation, operating systems cannot really do that very well. That goes to our second broad category, which is sometimes called virtual threads or green threads or user threads. There are various notions or names for this paradigm where the operating system has only a small number that's related to the number of actual resources of actual threads, but the higher level runtime, like the C++ runtime or the Java runtime, etc., is able to give the code the appearance that as if there are many, many threads, although the operating system manages only fewer ones. These are sometimes called lightweight stacks of execution that are cooperative with each other, typically because an operating system is not involved. These mechanisms do not have inherent preemption capabilities. But it's still very, very easy to write code that works with virtual threads if your runtime actually supports it. And the overhead compared to OS threads is much, much lower, which is cool. The main disadvantage of this approach, especially for our crowd, is that there is no standard support in C++ for this type of paradigm. There are various non-standard libraries and vendors that provide it, but it's not part of the standard at the moment. And the main reason why C++ standard did not choose to go that route is because this is not zero overhead. Again, the overhead is much smaller than operating system threads, but still the overhead of managing multiple green threads, multiple stacks, and switching between one of them is not zero overhead. So for that reason, this approach is not something that's available in C++ standard at the moment. And what's that? So with virtual threads, the context switches are typically done without the help or assistance from the operating system. It's what's known as cooperative scheduling or cooperative context switches, where only at specific points a typical virtual thread can stop and execution goes back to a different one. Okay? And then the last model, which is very common in really high throughput environments, is the notion of reactor threads or reactor thread pools. And reactors are basically just single threads that split all the work between them. And the basic idea is that I take my code, all the work that I need to do, and I find some ways to split it up, to chunk it up into various tasks. And the main thing is that every task on its own is non-blocking. Okay? And whenever I want to wait for an event, this is just something that happens in between tasks. So, and whenever, if I have a workflow that needs to happen, and that workflow needs to wait for several events as it runs, then someone needs to take this workflow, split it up into different tasks, such that whenever we want to wait for an event, one task completes, and the next task will only start once the event arrives or is achieved. So that's the basic idea. Then I can have these reactor threads, which are very, very low-level mechanisms, just know to run one task after another, and they know that they by themselves, each task itself is non-blocking, so whenever I start a task, I can very, very easily move on to the next one. And the various event reception mechanisms, such as network receivers or mechanisms that wait for user interaction, they are able to generate or enqueue more tasks into those reactor threads as they need. And again, the main benefit of this reactor approach is that it's a very, very low overhead mechanism. There's actually no operating system required. We can use the notion of reactor threads even in firmware or even in places where there are there's no operating systems. And very, very commonly, even if there's either just a single reactor thread, or we make sure that every different task or every different flow of operation can only execute on a single reactor thread at a time, which means that I don't need mutexes because I know that if my specific workflow is split up into various tasks, and even if right now there are 5 potential tasks that can be run, only one of them will actually run at the same time, so I don't need mutexes. It can make my life easier when implementing a system working in a reactor manner. Still, there are cons to this approach, and mainly it's the fact that something needs to take the work that I have that is in nature blocking, or in nature is very, very event-based or very, very reactive to potential events, and split it into tasks. And now the question becomes, okay, I want to work with reactor threads. How do I take some piece of code, some meaningful piece of code, and break it up into tasks that where each is not blocking? So we have various mechanisms to do that. One very common approach is the state machine, okay? Where I basically, instead of having a function that sort of like defines a flow, I can have a class that defines a flow, and the class itself will have different states, and I can draw the states in a diagram, etc. And there's also like the state design pattern, if you know about it. And whenever a new event arrives to my state machine, the state machine knows on which state it left off. So, and that existing state will be the one in charge of handling the new event, switching to a different state if needed, and then this state machine can go back to sleep, wait for next events to arrive. So this is very, very suitable for multi-stage protocols like handshakes, or dealing with like session control implementations, clients versus servers, where I know exactly how I want to move from state to state. And typically there are specification documents that actually describe those state machine transitions. And if the state chart is very, very complex, or if there's a lot of dependency between flows, and I cannot really split my work into different state machines that don't interact with each other, then things become tricky. And typical code that uses state machines will have just a large unordered map or some lookup operation that holds various state machines that are currently active or currently waiting for events. Whenever the reactor loop receives a single event, it performs a lookup to find the correct state machine that's relevant for this event, passes the event to the specific state machine, and that state machine will handle the event, switch to its new state, and get back to the pool, etc., etc. The next approach that is it's become more popular, especially with the rise of JavaScript, is the notion of callbacks and continuation passing style. So again, this is a notion where we write asynchronous operations, but we pass callbacks to those operations. And this way, I take my code and I basically, in a manual fashion, I split it into different tasks. Each is non-blocking, and I assign each and every non-blocking task to as the continuation of whatever events that it wants to wait on. And we'll have an example of such code in the next slide. And if you know the Boost ASIO library, basically until 2017 or 18, that was the main approach used by the ASIO library, where basically I can create and call whatever async operations I want. I attach the continuation, which should be non-blocking, or at least wait until the next blocking thing to it, and that way I create the change myself in a rather manual fashion. It fits very, very well in C++ 11, especially since we got the notion of lambdas and stood colon function, because that's a very, very common and very, very easy way to express my code of the continuation very, very close to the place where I perform my async operation. And it's very, very easy to pass around these pointers to objects that represent those callbacks. And if you look at the code with a little bit of squinting, you can see what needs to be sequential. We'll see that in the next slide. The main thing to realize or to know about when you're writing this type of code is managing object lifetimes is very, very complex. C++ is very, very rich with objects, and whenever I call an async function and pass it a callback, that callback might have pointers into other objects, or either in its lambda capture or otherwise. And we need to make sure that by the time the event arrives, all these objects are still alive. We need to know when to clean them up as well. And structured concurrency is basically a mechanism that is able to be a better approach than the ones that we discussed so far, and we'll talk about it in just a few minutes. So this is an example of continuation passing style code. I took it from the ASIO documentation. It's relatively small font, I hope you can see it, but basically we can see that we have the do-read and do-write functions of my session class. And do-read sort of like calls do-write whenever some data arrives. Do-write calls do-read after it completes writing some information. And it looks sort of like an infinite recursion, right? One function calls the other, but the do-read doesn't really call do-write. It just places some callback, some continuation with the ASIO library, and that callback will be invoked by ASIO when the event arrives. Similarly, when do-write is called, it will register the do read operation as the continuation once the write operation is completed. Again, lifetime is tricky here, and for that reason, we need to make sure that the session object that we're working on is shared, is something that can be held as a shared PTR, and we make sure to pass this shared PTR to all of these continuation objects, just to make sure that nothing gets destroyed too soon or too early, because otherwise those callbacks will point or need to work with something that doesn't exist here, okay? And again, this async function, it registers some event to happen with its continuation and returns immediately. Typically, writing code after this semicolon is a bug. Typically, if someone would expect this code to run only after the read operation is done, that's not true. And typically, once we register our events, there's nothing much else that we can do. We need to make sure not to do it. And now we come to structured concurrency. And the notion of structured concurrency basically tries to limit our ability to define what's possible and what's not possible when defining dependencies. When we try to take a single flows of information that can be asynchronous and perform some rules on them, make sure that they all adhere to some basic guidelines that make sure that we can handle them all in a very, very similar manner, especially to create composability. And when we have one orange task here, we can sometimes look inside it and understand that it's made up of different concurrent operations, but in other cases we can look at it as a black box from outside and consider it to be one single operation without thinking too much about how it's composed inside. So that's the philosophy. The philosophy is that tasks are resources with lifetimes, and the C++ crowd, and the C++ crowd already knows RAII. Okay, RAII basically says that if we have a resource, then the resource acquisition is initialization, is creation of an object, and resource reclamation or destruction is the destruction of an object. So every task basically belongs to a scope, okay, and whenever I create a subtask, it will typically belong to a subscope of the scope that I'm in. And the rule for structured concurrency is that every scope outlives and it will not get destroyed until all the tasks within it and within its subscopes are already complete or done, either successfully or with an error cancellation. And the analogy that we can think of is thinking about stud : jthread versus stud : thread. I don't know how many of you know the distinction, where jthread basically outlives, is a C++ object that outlives the actual physical thread that it owns. And the typical destructor of jthread will wait and join that thread, while stud : thread might let the resource dangle. So jthread is an RAI object and thread is not. And similarly for structured concurrency, those structured scopes are RAII, they will not destruct until everything inside them is done. So the main advantages, like RAII, is that we can many times visualize the concurrency and visualize the object lifetimes and the lifetimes of tasks when something is going to start and when something is going to end, by just looking at the code and looking at the braces. Okay, if we see a closing brace, we know that destructures might happen. Okay, we know that either every existing scope inside those braces will either be destructed or returned as sort of like a stud moved out of the brace. So I know exactly which scope is going to be over, and if I know that it's over, I know that everything within it will be done. I can destroy everything related to it. So structured concurrency is very, very similar to RAII, and similarly, it gives us a very hierarchical view of the world, a very composable view of the world. Again, we can look at different flows that I know are asynchronous and don't really care too much about what the level of concurrency within them, inside them, because all I need to know is that when this flow is over, everything inside it is over. And while the flow is running, anything inside it might be running. So that leads me to better composability. And I have this tree-style structure. You know, every task belongs to just one scope. Every scope that is a subscope belongs to another one. So I have this notion of a tree. I don't have cycles. I don't have fan-ins or fan-outs that are too hard. And for that reason, I don't need things like shared PTRs to manage lifetimes. It's very, very easy to understand when something is over and when something is complete. And also once we have that, then the entire notion of cancellation and error handling becomes much more intuitive. In a fork-based world where various threads are just created, or various asynchronous operations or callbacks are just passed or created, it's much less understood or much less organized when you try to think about what happened when errors occurred, or what do I need to cancel if a user tries to close the application, or if a user tries to cancel some subflow, because there's no notion of dependency or linkage or a notion of hierarchy between the different tasks. So it's very, very hard to understand if I wanted to cancel one task, which are the other tasks or which of the other callbacks might need to be canceled, where structured concurrency gives it this all relatively for free. So that's the structured concurrency philosophy. And one main takeaway that we can learn today is that coroutines in C++ are structured concurrency. So just a short reminder of coroutine mechanics. Whenever we run or invoke a coroutine function, that call doesn't actually typically run anything. It doesn't actually run the code inside the coroutine. What happens is it just creates a task. It creates what's known as a coroutine frame. And that coroutine frame is typically just sitting there. It can start some execution, but it can also suspend. And I can do whatever I want with it. And so there is very much similar to an async operation, right? But then I can have this, I have this handle to this coroutine frame, and I can use it. And inside the coroutine, whenever I have these calls to co-await, those are places where basically I can basically tell the infrastructure that I'm ready to suspend. This is a place where some outside event might take place. I'm ready to suspend. And in fact, I see that Adi's in the crowd. Adi had a very, very good talk, maybe even 6 years ago now, describing how the compiler takes a coroutine function code and turns it into a state machine. Okay, so if I write a coroutine with co-awaits, I basically the compiler does the heavy lifting of converting my code into state machines without me needing to worry about it. And again, once I suspended, the coroutine can be resumed later at the exact state where it left off. And there's totally legal, totally viable to also destroy it without reaching completion, which is sort of like the notion of cancellation. And both resumption and the destruction of a coroutine can be very, very easily facilitated with the notion of the awaiter object. That is sort of like the one that manages the co-await operation. And the awaiter object exists as part of the coroutine frame in the suspended state. And it is consulted if you want to either resume or cancel the coroutine. And this, so this is the place where the link between a single coroutine and its sub-coroutines or subtasks can be created. So whenever I have a coroutine, it has it currently has awaiters because it's suspended and it's waiting for other subtasks. The awaiter can see all the, or knows all the other subtasks that it might be relying on or dependent on, and when it gets destroyed or resumed, the awaiter knows exactly how to deal with them and create this philosophy, this rule of coroutines, of structured concurrency, where all subtasks must cannot leave more than their parents. So the instruction deals with cancellation and completion, and await resume can also handle error scenarios in a very, very nice fashion. I should note that co-await looks like a one-to-one relationship. I have a coroutine where I wait for one event, and then I go, and then I return, then I wait for another event and return. But that's actually not the case. So, co-await can also be used to wait for multiple events, to perform fan-out, and use parallelism as I want it. And there's actually an experimental feature inside the ASIO for operator ampersand ampersand, operator or that allows this type of composition of fanning out. And there's a good talk from CVPCon 2022 by Danielle Engert, where she spent some time talking about this magical operator or, which basically creates this sort of a race. It engages waiting for two different events. The first one that happens is the one that we care about. The other gets canceled, and we can this way create these fan outs and fan ins very, very simply. In this case, she creates a race between a read operation and a timer. Okay, so that's what we have here, and we can co-await this OR expression. Great. We talked about coroutines. Let's talk about senders. Senders are this new library, new mechanism that we're going to get in C++ 26 for executions of concurrent actions. I don't know how many of you have already seen or heard of talks about senders. This is not meant to be a primer on senders, but if you like, and we have some time, we can talk about it after the talk. But basically, those are senders are these notions, these objects that also represent asynchronous computations. They are mainly built for describing tasks of asynchronous operations that need to be done. And the main thing that one can do with a sender is to compose it. Okay, so a sender is sort of like an async execution. You can think of it sometimes sort of like a promise or something like that. But the main thing is that there are many, many ways to take existing senders that represent asynchronous operations and compose them together into larger and larger computation trees that are all asynchronous and have different events and tasks in between them. So each and every leaf, so to speak, in the sender is some non-blocking code. And the connection between senders themselves, that is what can create these breakpoints that allows us to benefit from concurrency, benefit from asynchrony. So the sender adapters are this notion that guarantee the structured concurrency. Whenever I take several senders and compose them into subtasks of one single sender, using one single sender adapter, that sender adapter is coded in a way that ensures the philosophy of structured concurrency. It will make sure that the sender adapter that engulfs or encapsulates several subtasks within it will not complete before all of its subtasks complete, etc., etc. And similar to range adapters, when we create this composition, when we compose different senders together, no actual work is done. We sort of like create an onion. We create a combination of one sender composed of different senders within it. And this onion represents the entire calculation graph. And we'll see it a little later in the following slides. And again, if you look at it from the outside, we can consider it as a single operation. But if you want, we can peel in the onion and see the different subtasks within it. Senders are more bare bones than coroutines. Using senders is more complicated than using coroutines. It's a little bit of a more low-level mechanism, a little bit of a more low-level structure. So it's harder to, at least for now, to use the senders as they are. But they give a little bit more power because they are closer to the bare metal. There's more direct interaction of senders with the actual operating system or scheduling or other mechanisms. If needed, there's less need for these awaitable notions of coroutine frames, etc. If people know their coroutines, they know that there's no guarantee in the standard whether a coroutine frame needs to be allocated on the heap or not. If you write code using senders, you have much more control. You need to do a little more work, but if you want to avoid heap allocations, you can do it. You need to do it yourself, but it can be guaranteed because it's all on you. And the key insight is that senders are actually awaitables, and awaitables are actually senders. So whenever in a code base I have a sender adapter that needs to adapt the various other senders, I can provide it an awaitable, a coroutine awaitable, and use that. And the other way around as well. If I have a sender and I'm inside a coroutine, I can co-await that sender, and it all works. It's very, very good for interoperation. That basically means that if I right now even don't have a sender framework and I start taking my system and write it with coroutines, I know that I'm not locking myself into one world and avoiding the other, because these were both meant to work together with each other. So this is a slide from a talk by Bryce Edelstein-Leibach from 2022, where we basically showed a little bit of this onion thing, where, again, if we use, we have some sender that describes some asynchronous work, and I use the pipe operator to perform some continuation on it, and another pipe operation to perform some continuation above it. Basically, what I get created is this sender object that's the result of this entire expression, where one of its members is this sender of the Zen, the result of the Zen operation, and inside it we have the result of the before operation, and that before by itself can have more and more layers in the onion. And this chain of senders describes work that needs to be done. And once I initiate the work, there's some connect operation that takes place, which basically creates receivers in the exact opposite order, and that order is the opposite where we want computation to actually take place. And once we have this opposite onion of receivers, I know that first I need to maybe communicate with the outside world, maybe with the hard drive or a database or something, and wait for the before event to happen. Once the before event happens, then the receiver knows it can peel a layer of its shell, pass that information or the result to the then operation for it to work on, and that operation, once that's complete, we can move to the after operation, etc., etc. And once every layer of the receive onion gets peeled, once the specific event that it's waiting for is ready or available, and when the entire chain is complete, then this entire receiver onion is destroyed, and we have the result of everything back in our hand. Okay, so let's look a little bit at some code to understand what we're looking at. And the basic idea, what I want you to take out of this slide, is that when we look at code that's either coroutine-based or sender-based, I can see the chain, I can see the flow of operation in the code itself, and I don't need to look at too many callbacks, too many lambdas, etc., etc. So this is some example from ASIO of a coroutine-based asynchronous operation. So again, so this echo server is a coroutine. As we mentioned, it returns an awaitable. It's an async operation. And what we have here is an infinite loop that has two sets of wait points. One for async read, one for async write. Basically, reading some information from a buffer or into a buffer, and then sending it out to back to the same socket. We can see that the data itself that's being used is this variable here. And let me ask you, this data variable of 1024 bytes, where does it live? Is it in the stack or on the heap? Where does it live? Yeah, that's true. So people answered that this looks like an automatic variable, but it exists in the stack frame, on the coroutine frame, sorry. And the coroutine frame can live either on the stack or on the heap based on the compiler's implementation. So if the compiler can prove that this entire coroutine will not outlive the function that called it, it can actually put the frame on the stack itself. If it cannot prove it, then the frame might go to the heap, and then that's where the data will reside, but the code itself doesn't clearly show it. Here's the sender implementation of a similar function. It's not the exact same echo function. This is just one part of it, okay? This screenshot is taken from Robert Lee's talk from Core CPP from last year. We can see this read function, or read async operation, that basically receives an object that one can read from in an asynchronous fashion, and tries to put or to fill the bytes from that readable object into some span that's existed, or we were given up until now. And what we can basically see here is all these pipe operations. Okay, these pipe operations is the composition of senders, and we have different types of sender adapters that work for us. So let's see how the code looks. We start with just passing the span from the regular synchronous world into the asynchronous sender world using the just keyword, and then we take that span and also the readable object by reference in order to start our own pipe that runs repeatedly, one time after the other, until some predicate happens, until the span itself is empty. In every iteration, we'll try to read some information, put it in the start of the span that we have so far, use subspan to shorten whatever remaining data we have, and once everything is ready, the span will be empty, and the repeat effect until will complete. And the repeat effect, so this is the predicate, and this is the action that needs to happen in each iteration. So we start with just doing nothing, and then we read some operations, some value from the readable that we have. This is an asynchronous operation by itself, and then once we had the data, we can deal with it, look to make sure that if there are any errors, and deal with the errors, etc., etc. So That's what we have. You can see that there is some similarities in the code, but it's obviously different. And I would say that the left side is more readable to me, but with time I might find both as readable. The for loop becomes this repeat effect until. Managing the data in the coroutine world looks like accessing a local variable. Well, actually, we know that it's just part of the coroutine frame, whereas in the sender world, these are just pieces of information that we need to convert or move from the synchronous world into the asynchronous world and pass either by reference or by value across the chain to every piece of, or every component in the chain that needs it. And that's the way we can write or create code in one manner or the other. But in both cases, we can see that we can read the code from top to bottom, and we know that the execution flow will be as we read it, even though it will not, there will be actual places in time where things will block and need to wait for an event to happen. So whenever we see a co-await on the left side, or just even a pipe on the right side, we understand that this is a place where potentially things will block, need to wait for some other event to happen, and then that event happens, etc., etc. Okay? So here's a summary so far. We talked a little bit about concurrency and about structured concurrency. So again, concurrent systems are meant to handle complex scenarios of incoming events. Getting high performance means eliminating as much helper facilities as possible, eliminating stacks, eliminating heap allocations. And for that reason, we don't want to use high overhead mechanisms, and we want reactor-based patterns. And the older approaches for reactor-based patterns were relatively error-prone. We had to deal with a lot of attention regarding object lifetimes, regarding errors, regarding cancellations, etc. And structured concurrency is meant to be a solution that gives sort of like the best of both worlds, giving us some relatively easy or relatively organized way to think of our asynchronous code, but also keep it high performant with low overhead. And again, similar to ranges, by the way, the main value that we get is the value of composition. We can take these senders or take these coroutines, break them up into subcoroutines with relatively low extra cost. And again, both frameworks provide structured concurrency, and we can mix and match them as well. We don't have to choose one. Okay? So now I have just a few minutes talking about taking existing code and migrating it to structured concurrency. I have to tell you that I'm happy that I don't have a lot of time to talk about it, because I don't have a lot of insights to give you, except that it's something that we actually should do and we want to do. So no silver bullets, just a few tips. So first of all, don't take on too much of a challenge. Remind yourself that although the standard itself is relatively young in both these fields, but there's actually quite a lot of existing good quality code out there that you can use. So start with taking an existing library from the open source community and bring it into your project. ASIO is a very good candidate. Since C++20, they've implemented and started modernizing their library to work with coroutines. CPP Coro, another very good coroutine library with a lot of notions that might land in the standard as well. Cobalt is the Boost's attempt of creating a coroutine library. And when it comes to standards and receivers, again, they are not yet in the standard. They were voted in to C++26, but there are already several good implementations. I think the best known and best battle-tested one is the one by NVIDIA. And there's also one in the BMAN project, which tries to be as close as possible to whatever is going to be standardized. There's also a BMA.NET project that aims to create a standard framework for network, which will sort of be more standard conformant than ASIO. But it's, I think, relatively young and not as battle tested as ASIO. Now, again, once you take this library in, you still have a working system. I would try to encourage you to try and keep control of your main loop if possible. So if you already have a main loop, if you already have a reactor core loop, try to keep control of it. So the ASIO IO context, for example, doesn't have to take control of its own thread. You can use its poll method to also work in a non-blocking fashion. So you can take a system that has its own reactor threads and add in ASIO without affecting, without the need to create more threads, or without inverting the control from your thread to someone else. Yes, there's a question here. What's that?
One of them are RT-friendly.
RT-friendly?
Real-time friendly.
Oh, so the question is whether any of these libraries are real-time friendly. So I'm not an expert on that. I actually want to refer you to some talks by Ben Dean and Michael Case, who wrote and open sourced a sender-receiver framework for very, very low-level firmware-related systems like interrupt handlers, et cetera, So go and look for talks by Ben Dean and Michael Case about their firmware-based sender-receiver framework, okay? So where do we start? I would personally start with coroutines. Okay, coroutines are already in the standard. There's a lot of experience in them. There are quite a few libraries that exist. As you mentioned, if we're trying to take our code and migrate it toward coroutines, we're not going to regret much of it later because it's still going to be mix and match. Things are going to be work together. If our current code is already non-blocking, if we already have a reactor core, I would consider starting from the root and not the leaves. So try to take one of like our root functions inside the call stack of the reactor and converting it from being a function that returns void or that has an endless loop into a coroutine. First of all, whenever when that function calls return, we'll just co-return. So whenever we handle an event in the old world, we returned control back to the reactor. Now we just co-return and get back to the reactor and sprinkle where I can add co-await inside those root functions in a gradual fashion. Okay, so I start with taking one of my non-blocking handling functions that already has many returns because it has a state machine. Convert the returns to co-returns, and then try and convert some of the co-returns into co-awaits by simplifying the state machine within them. If our current code is blocking, like threads or things like that, I would try to go from leaves towards the root. And again, in here we have the typical problem where known as a function coloring problem. If I have one function that currently is non-blocking and has a return, I convert it into a coroutine. Suddenly whenever anyone calls it, it needs to also become a coroutine. Whenever anyone calls that, it needs to also become a coroutine. So we have two different colors of functions, the non-blocking functions and the coroutines, and it's very hard to avoid this propagation, so you need to be creative sometimes on these types of things. And one last tip is don't be afraid of cancellation. The cancellation mechanism, both in coroutines and in centers, is something that exists and can be used, and it should be relatively straightforward to use. And so if I have some old and new pieces of code, the old code uses coroutines or doesn't use coroutines, and the new one does, so it makes things hard to interact with. I cannot touch inside a suspended coroutine. At least I can cancel it. I can cancel it and do something else instead. Alternatively, I can try and be creative with whatever co-await returns. Instead of co-awaiting for an event, I can co-await for like a variant of either the event or something else that popped in from somewhere else, maybe using stood expected. Okay, so these are some initial thoughts of where to start. Yeah?
Are these recommendations for the code which already use parallelization, right?
Yeah, so basically,
it's not about the code which exists, which is not in any level of parallelization, and now to convert it to parallelization using coroutines and something like that.
Yeah, okay, so the question is, am I talking about taking an existing concurrent system and migrating it to the new framework, or taking a non-concurrent system and making it concurrent? And the answer is mostly on the first one. Okay, taking an existing concurrent system and gradually making it into a structured concurrency. If my world is one where I have a non-concurrent system, I want to convert it into a concurrent system, I think the problem is a little simpler typically. Because at least I don't have two concurrent frameworks that sort of like intervene with each other. Yeah. Okay, so that's basically some of the tips that I have for you, and an introduction to concurrency, to structured concurrency. So again, structured concurrency is a paradigm shift. Okay, we need to think a little bit different about how we write concurrent code. It looks like it sort of like binds us into stricter rules than what we're used to in a very careless callback or continuation passing style mechanism. But once we do that, the experts tell us that our lives will be much happier and safer from problems and issues and bugs. If we use correctly, it will make our code more readable, more safe, and with lower overheads. And in C++26, we'll have basically two mechanisms to use structured concurrency, and I'm most welcome you to try and do it. Coroutines, again, relying on third-party helper libraries, and senders as well. And now is the time to start start our preparations and migration right in front of the standardization being completed. So thank you very much. I'm happy to take questions. Yeah.
How are senders and receivers not a step back from coroutines? Because they seem much less readable. And I guess that's the question.
Okay, so the question is, how are senders and receivers not a step back from coroutines because they seem much less readable? So I tend to agree with you that right now they seem less readable. The thing is that the way I see it, senders and receivers are a little bit of a lower level than coroutines. They give you a little bit more control. So if you work with senders and receivers, you need to write a little bit uglier code, but you have much more control. And happily, because of the interaction, you can go with coroutines whenever it fits you, and whenever you want or decide you need a little bit more control, then you take that specific part, convert it into senders.
Most of the libraries that offer scheduling, some of them I think you showed, already have that then concept, which is pretty similar to sender and receiver, right? Like and then chaining the continuations on top of each other.
Yeah, okay, so the question is, does the calling a .then function on a future also give a structured concurrency? And it really depends on the specific libraries. The main question is, does the lifetime of the subtask able to outlive the task itself, etc., etc. But I think typically if you have a way to do continuation, it can be classified as structured concurrency, yes. Yes?
Is there a way to convert task graph style concurrency into structured concurrency? Right now I have a system where we just create all of our different sections and then combine them with declaring predecessors. Is there a way to turn that into structured concurrency? Or is that going to have to stay its own thing?
Okay, so the question is about converting task graphs into structured concurrency. I'm not an expert there. I think the studexec library from NVIDIA has some attempts to integrate with TaskFlow, if you know it. But I guess maybe we can talk offline. So I think I'm out of time. I really, really thank you. I hope you had a good time. I sure did. So thank you very much.